Okay, well, I think I'll just start with a comment that this is going to be an overview. It's intended as an overview, and I'm covering a lot of material. And if your favorite material is not in here, it's not because it's not important. It's because I had so many things to cover. There's a lot of stuff to do in this area. So I'm going to be talking about in general a technology roadmaps, where do we need to go and when and that sort of thing. Um, let's see. Oops. I do have an abstract and information in the presentation that is already uh, let's see, that was already in the flyer, but that's for reference. I'm going to be talking a little bit about motivations, more about superconductor electronics, and most about superconductor electronics, then a little bit at the end about quantum information processing. So why are we doing this? Well, there was a time, this was about 10 years ago, when we were even over 10 years ago, when I was supporting the government. We were looking at some problems with just the amount of energy usage that's going into computing. And even then, it was clear that the amount of energy was just getting huge. And the number of solutions, for instance, this data center that Facebook was building um, in Luleå, Sweden, um, uh, there weren't a lot of places like this where you get some free cooling and they have a river with excess hydropower, and it looked challenging. That situation has not really changed. Now, it's not so much Facebook these days, it's AI, machine learning, uh, things that are gobbling up the power. But it continues to be a serious problem. So, yeah, we got a problem. And at that time, it looked as though superconductor computing was promising, and we were able to sell a program, so-called the C3 program, cryogenic computing complexity, that on paper looked like could have some significant benefits, especially in power and size. And the big problem that we had with that program was memory, and memory continues to be a problem. So the need is still there. Solutions are still waiting. Um, there have been developments such as D-Wave. They still have the most complex in terms of Josephson junction count, little over 1 million Josephson junctions on a chip in their quantum processing unit. And there are many other companies that are working in this general area of quantum computing. Examples, Google, and you've seen things like this, where there's lots of wires going down into the cold space, and we really need to replace those wires with something else, with circuits down at cryogenic temperatures. And we think that that's a big potential application for superconductor electronics. I'll talk more about that later. The vision is that eventually there will be a hybrid of technologies, whatever works best. And there's going to be a combination. And we think that it's quite possible that uh, some sort of superconductor electronic processing will be can be a part of that. However, how much a part of that depends a lot on this audience, how innovative we are, and how much we can do to create solutions. So Roadmap. There is something called the IRDS CEQIP report. This is the International Roadmap for Devices and Systems. This is something that took over from the old ITRS, International Technology Roadmap for Semiconductors. Now we no longer care where the solutions come from. They can be optical, superconducting, semiconductors. It doesn't matter. We need solutions. And I lead an international focus team on cryogenic electronics and quantum information processing. And the 2023 report is currently available online. 2023 included the first, well, I'll say the coverage that we include superconductor electronics, which I'm going to be talking mostly about in this talk, cryogenic semiconductor electronics, I'm going to skip, and I'll talk a little bit about quantum information processing. And in the 2023 report, we had the first roadmap for superconducting quantum computing. And we're still hoping to work on one for ion trap quantum computing in the 2024 report. However, that's outside of this talk. And so examples of what we talk about, um, superconductor electronics. This is the section on superconductor electronics. And we are focused on, we start with applications and market drivers. So the new roadmaps, the roadmap IRDS is driven from the top down, meaning the demand, and then from the bottom up, sort of what we can build and new circuits and devices and methods for doing computing. So in the 2023 report, the biggest area of update was quantum computing that has become really a driver for what we are doing. Present status. So we survey the technology, and then we also talk about active research questions and roadmaps. Here's just an example of figures, different, these are devices for switching. And they're switching devices, they're memory devices, and we just monitor the status of these things. And we talk about what is needed. Okay. Status summary, it's still developing technology. It's just got a small market, big promise. Quantum information processing is an emerging driver. Logic, there's many competing approaches. I'll talk more about that. Memory, little available, no clear solutions. I'll talk a little bit more about that. And then fabrication, there's research mostly and some commercial fabrication. Key needs, there's a lot of them. Power supply, we really need a better way to supply our circuits. Sensitivity to magnetic fields, currents, trap flux. We need to reduce the area, logic, memory, fabrication for scale, testing. EDA, electronic design automation, design is also a need, but it's not on this list. It's a little bit less than of a need than some of these other areas, but it's in there as well. So logic, we're still searching for a winning combination. This is similar to our current status, is similar to semiconductor logic families, maybe back in the 1960s, where there were a variety of logic families all competing, and all of them had advantages and disadvantages. By the 1980s, that had come down to late in the 1980s, CMOS won out. And our situation for superconductor logic 2010, this is even now 2020s. We've got the situation where there's many, many different logic families, including some new ones, and it's not clear which one is going to win out. And what we do is monitor the considerations. We're trying to guide people towards logic families that have the most promise. This is an example table, and what this is showing in the red is that the number of devices per ampere, when you're less than, 10 million, 100 million junctions per ampere, that tells you that it's not going to scale. So these are all like the DC powered approaches. Mostly the DC powered approaches we just don't think are going to scale. And then there's other things like transformers and clocked gates and things that we're looking at as well, and the variety of devices. We're still working on how we present this, and there's a need to separate the logic from the power delivery. Right now, these logic families have assumed power delivery approaches with them, and we really need to separate them out because there can be logic that with a better power delivery approach would scale better. But we still haven't found what I consider to be the CMOS for superconductor electronics. Okay, memory. We also monitor memory. The numbers are really small. These are bits, and the numbers are very small. We really need a better memory solution, and so and there are prospects. I'm not going to cover them here today. Benchmarking and metrics, we do look at the benchmarking and how we can compare against other competing technologies. For instance, we look at commercial approaches for refrigeration and how that scales with temperature and with size. So, and we have ways for comparing against cutting edge logic approaches. There aren't a lot of advantages for superconductor electronics unless you have to operate cold. If you have to operate cold, as you do in a quantum computing environment, then there can be significant advantages. The real advantages, I'll just skip through here, is that you really get huge advantages over conventional technologies when you include the interconnects. So interconnects greatly improve things, and especially, that over distances. So, of course, interconnects are the big win. Let's see. We monitor fabrication processes. And this is just an example of this, most of the characteristics. We have a little bit of commercial fabrication, and but there's only for 300 millimeter, there's a few 200 millimeter fabs, and then for 300 millimeter, it's just exploratory work that's being done. So there's needs for development there. Let's say